Guys, the center of mass is a particular point in a system or in an object. And this point will move as if all of the mass of the system is concentrated at this particular point. So typically, if we apply some external force at this particular point, then we think about all of the mass moving then at that particular point. So we symbolize mass to be thinking of pretty much the total mass of the system. So we're going to symbolize this mass as a capital M. And we think about that mass, this capital M, located then at the center of mass. So just again, this capital M is just representing the total mass of the system. And that's where we think of all of the mass of the system concentrated at a particular point. Thus, we call it the center of mass. This behavior, this center of mass, where the mass is concentrated at a particular point for a system, this is independent of other motion. So we'll talk about in the next chapter with rotation, or later on in this chapter, the deformation of a system. Of course, we can write center of mass in terms of coordinates or in terms of components. We have coordinates for the center of mass. If we think about the center of mass in the x direction, then we should have a sigma out in front of all of these as well. So the formula here, if we just look at right now the x direction, because ultimately all of the directions are going to be the same. So if we break apart, we have the sum of mass times the position in the x direction. And then all of that is divided by this capital M, which remember on the last slide we just said represents the total mass of the system. So ultimately what we're doing is we're breaking apart and taking the sum of the masses times their position in the x direction, and then we're dividing it by the total mass. We're doing that for each y and z as well as for the x direction. Now the center of mass of a system is usually located somewhere between two particles, and is, if we're looking at specifically this example here, we could say that the center of mass of this system is located somewhere on this line, and that line is just joining the two particles. And it's going to be closer to the particle that has the larger mass. Let's say that we want to calculate the center of mass here. So let's say that at x to the first, that one is going to be at a distance of 0. And then let's say that from where we had, let's say that x2 is going to be at a position that we'll just call d, some displacement. And let's say that m2 is equal to 2 times the mass of m1. Now, if we wanted to find the center of mass for this, then we can think about all of this is happening in the x direction. So let's use our center of mass for the x direction. I know then that I have mass 1 times the position that mass 1 is at, which would be just 0. I'm going to add that because it's the sum of the masses times their positions. So mass 1 times its position, which is 0, plus mass 2, which we just said was 2 times the mass of m1. So let me say 2 times the mass of m1 times its position, which we said that for the second mass, its position we're just going to call d. And then all of that is over the total mass, so that would be m1 plus m2, but again, we said that m2 is equal to 2 times the mass of m1. If I simplify this down, that would give me m1 times 0 just be 0, so that would leave me, I'm going to move kind of over here, guys, sorry, so 2m1, so 2 times the mass of the first particle times that distance over 3m1. Well, my m1s can cancel, so then that means that my center of mass, if I'm thinking about it in the x direction, is going to be equal to 2/3 times that particular distance. So the center of mass of any symmetric object that has uniform density usually lies on an axis of symmetry and on any plane of symmetry. Well, let's say that we don't have necessarily a symmetric object, more we have some type of an extended object. Well, we can do a similar analysis on an extended object. If we just think about some extended object as a system that contains a large number of small mass elements. So we think again that we know that this system is made of many particles that contain some mass. So let's just say that we have a large number of these small masses here. Now, since the separation between these elements we can think about to be very small, then for us we can safely assume that an extended object is going to have some type of constant mass distribution. So it will be very similar to just how we would do even just an object that has some amount of symmetry. We will still model the object as though it has a center of mass, but in this case we just think about that mass in the extended object to have a constant distribution, even though it may not technically, we'll just assume. So the center of mass in 3 dimensions can be located by its position vector, which we will denote as r, and then the subscript cm to represent that it's the position vector for the center of mass. For a system of particles, we already saw this when we were looking at the particular components, the x and the y and the z direction. Remember we said that if we're thinking about the center of mass in the x direction, it was the sum of the masses times their positions over that capital M, over the total mass. Guys, it's the same thing here. So the position vector for the center of mass is equal to 1 over that capital M, which again is just representing total mass. And then we're going to multiply that by the sum, that's a terrible sigma, by the sum of the masses times then that position vector. So in case we forgot what the position vector would look like, remember that's going to be the x direction with the y direction and the z direction. Finally, let's say that we have an extended object where we are assuming that we have a constant mass distribution. Ultimately, that's going to be my 1 over, again, the total mass times the integral of the position vector in respect to mass, so r dm. So like we said, for center of mass, that's just a particular point at which we like to think that all of the mass of the system is concentrated, and it can move, this object can move as though that is the area, that is that particular point where that system has a mass that's concentrated. The center of gravity is a little bit different because we know that each small mass element for an object is going to be acted upon by a gravitational force. So the net effect of all of these forces that are acting on these small mass elements, is equivalent to the effect of a single force. And that force, again, we just know is the mass times that acceleration due to gravity. But particularly, center of gravity, we think about the total mass times that acceleration due to gravity. So the net effect of all of these forces acting through a particular point is what we call the center of gravity. Now, if the acceleration due to gravity is constant over the mass distribution, then the center of gravity will coincide with the center of mass. But if an object does not have a constant acceleration due to gravity over mass distribution, then center of gravity and center of mass will typically be at 2 different points. If an object is pivoted at its center of gravity, then it should balance in any orientation. So usually we can find the center of gravity by the following bullet points here. So it says that we can suspend the object from one point. So in this particular example right now, we are suspending the wrench first from this point here, A. Then we're going to suspend this object from a different point. So at first we suspended it at A, and now the next point that we're going to suspend it from here is at point C. We find that the intersection of the resulting lines, so the intersection between where I first freely hung the wrench at position A, and then where I hung it from position C, that intersection between those 2 points and halfway through is going to be then my center of gravity. So finding center of gravity is a relatively easy process for different objects. Determining center of mass is a little bit more difficult. So let's do an example where we have multiple particles in a few different directions. So a system consists of 3 particles. So we have M1, M2, M3. Find the center of the mass of the system. Now it says that the masses are given here. So we know M1 and M2 are equal. They're both 1 kilogram. And M3 is going to be double that. It is 2 kilograms. So I'm going to make a new page to show all of the work for this. So it will kind of help out more if you have these printed off. So then that way you can kind of follow along that way. Okay, so in this problem, I have some particles that are in the x direction, and I have some particles that are in the y direction. So let's just first think about the particles that we have in the x direction. So I could say my center of mass in the x direction, like we said, is equal to 1 over the total mass times the sum of those individual masses with their positions. So ultimately that's the same thing as saying M1 times the position of that first mass in addition to the second mass times the position of the second mass plus the third mass times the position of the third mass all over the total mass, which is just M1 plus M2 plus M3. Okay, so we know that mass 1 lies on the x-axis. So we can say that for the first mass, we know that that was 1 kilogram. And the position of the first mass was at 1, well, that was in meters. So it was at 1 meter. So I'm going to write 1 kilogram times my 1 meter. So that would be my M1 times x1. I'm going to add that to the second mass. For the second mass, we know that that still had a mass of 1 kilogram. And we know that that was at a position on the x-axis of 2 meters. So here's my M2 times my x2. Plus, now I need to think about the position again of my third mass, which was M3, and that was 2 kilograms. But its x position is actually just at 0. So I'm going to take all of this and divide it by the total mass, which is 1 kilogram, plus the mass of the second, which is 1 kilogram, plus the mass of the third, which is 2 kilograms. So if I simplify all of this down, my x direction's center of mass should give me 0.75 meters. Guys, we can do the exact same thing for the y direction. So if we do the same thing for the y direction, our center of mass in the y direction is going to give us 1 meter. So then if I want to write my center of mass in vector notation form, that's going to give me 0.75 I roof plus 1 J roof, and that will be in meters. Alright guys, so in this example we want to show that the center of mass of a rod of mass M and length L will lie midway between its ends, assuming that the rod has a uniform mass per unit length. So because they say that it's uniform, we could argue based on symmetry reasons that we should get the center of mass to be equal to 1/2 times the length. So ultimately, that's our goal. But let's say that we could divide this rod into very small mass elements, and then that way we could use the integral version instead to show the exact same thing. So if I divide the rod into small mass units, then I could say that each of those small mass units is going to have a length that we will call dx. And the other thing that we need to know for this problem is that there's a quantity in physics that we call the linear mass density. And the linear mass density is symbolized by lambda, and that is equal to mass over length. So linear mass density is also symbolized as lambda, and that's just equal to mass over length. So again, if we divide our rod into smaller divisions, then again we can think of those small divisions as having a length of dx. That also means then that we can think of the mass as dm. Now that would mean that lambda equals dm over dx. And then that would mean that dm is going to... Sorry, guys. That also means that dm is going to be equal to lambda dx, which is what I see right here. Now, we know that our formula to find center of mass, and this is pretty much all in the x direction, so we can think about center of mass in the x direction is equal to 1 over the total mass times the integral of x dm. Okay, so we know the dm is actually equal to something else, so let's plug that in. So that's also equivalent to 1 over m times the integral of x times lambda. These are terrible, guys, sorry. Let's try over again. 1 over m times the integral of x times lambda dx. Okay, so let's also rearrange this because ultimately the linear mass density for this object should remain constant. So I could pull my lambda out of my integral, so that would be lambda over the total mass times the integral of x dx. But what are my bounds here? So ultimately, if I'm looking at my graph that they gave me here, this rod is lying on the x-axis. So we could say from 0, because it looks like we're starting at the origin, to ultimately L, which is representing then the length of that rod. Okay, so if I integrate then for x, that should give me x squared over 2. And again, those were my bounds from 0 then to L. And ultimately then my x then becomes L, so then let's simplify this down. So I have my lambda over my total mass, so lambda over m. And then that's also going to be multiplied then by L squared over 2. Okay, so this would look like lambda L squared over 2m. Well, I also know that lambda is equal to mass over length. So let's plug that in for lambda, because then that will simplify some things for us as well. So I have mass times length squared over 2 times my length. And then also times mass. So again, this m divided by L just came from the fact that I was plugging that in for lambda. Okay, so ultimately masses are going to cancel here. One of the L's will cancel, so this 1 in the denominator is now gone. I'm left with just 1 on the top, so L over 2 is then equal to my center of mass, or we could say 1/2 times the length. So we know that since this says that this is a uniform rod, and if we assume that it's symmetrical, it should have given us a center of mass to be 1/2 times the length. But we found that even if we do the integral, if we break apart and divide the rod into small mass elements, that we will still get the center of mass to be 1/2 of the length. Guys, we can also describe the motion of a system of particles if we think about also just the center of mass. So let's just assume that the total mass for all of the particles, again, is just as symbolized with a capital M. And let's say that that total mass of the system is going to remain constant. We have to assume that for the following things to be true. We can describe the motion of the system in terms of velocity. We could also describe something in terms of acceleration for the center of mass of the system. So in the first part, we can see that the center of mass for the velocity of the center of mass, we know that we can just take the derivative of the position to give us velocity. Or I could say then that's equal to 1 over the total mass times the sum of the mass times that center of each of those individual velocities. If I want to think about momentum, then I could say that the momentum is equal to the total mass times the velocity of the center of mass. And that's going to equal then the sum of the masses times those particular velocities of those individual masses. And then that's going to also equal the sum of the initial momentums, which can also just equal the total momentum. So the total linear momentum of the system is just going to equal the total mass multiplied by the velocity of the center of mass. So my linear momentum, if I'm thinking about total linear momentum, is equal to the total mass times that velocity of the center of mass. Guys, again, we can find the acceleration of the center of mass, and that's just differentiating velocity with respect to time. So I can take my derivative of the velocity, specifically center of mass, over time, and then that's also just equal to 1 over then the total mass times the sum of the masses times those individual accelerations of those masses. We can also relate this center of mass acceleration to force. So if we take the total mass times that acceleration of the center of mass, that should equal, it's a terrible sigma, guys, that should equal my sum of forces. So I can say that if I have an external force present, that the net external force will equal the total mass of the system, so there's my capital M there, multiplied by the acceleration of the center of mass. So none of these ideas are new concepts. So we know that if we differentiate velocity, we're going to get acceleration. We know that if we differentiate position, we're going to get velocity. We also know that according to Newton's second law, force, if we're thinking about net force, is equal to mass times acceleration. So none of these concepts are new to us. The only thing that's new is saying that we're talking about a particular center of mass now for a system.